Quantum physics has a reputation for being hard to understand. It is full of counterintuitive and slightly mysterious ideas. It is, after all, the physics of things that are so small they are usually invisible to us. So how do scientists go about illustrating quantum physics? How do they draw things that can't be seen? I've raided the physics shelf at the library and found some books that do a good job of visually explaining quantum weirdness. These are written for university students, so they don't shy away from the complexity. My own physics knowledge is pretty rusty, so when flicking through these, I just wanted to see how much I could remember and if I could learn anything new just by looking at pictures. I did learn some new ideas and got a good refresher on others, so I'm going to share my favorite illustrations with you. They start simple and get more abstract, working up towards quantum logic and ways to torture atoms. Thanks to Brilliant for sponsoring this video. They've just announced a new Brilliant tutor that helps you learn without telling you all the answers. More on that later, and there's also a link in the description. This first book is Quantum Physics, Illusion or Reality by Alistair Ray. It starts by illustrating one of the core questions in quantum physics. What is light? Is it a particle or a wave? Here it is shown as an electromagnetic wave consisting of rapidly oscillating electric and magnetic fields, which are at 90 degrees to each other. And then there's the double slit experiment. Light that reaches the screen, C here in the diagram, could have come through either slit A or B. If the two paths differ by a whole number of wavelengths, the waves add and reinforce. But if the path difference is an odd number of half wavelengths, the waves cancel. So this is an illustration of constructive and destructive interference. But some other experiments, including those regarding the photoelectric effect, indicate that light isn't just a wave, but also has characteristics of a particle. So if light is made up of particles, then maybe in that previous double slit experiment, it wasn't wave interference, but rather particles bumping into each other that led to that effect on the screen. So this next illustration shows an experiment where photons, particles of light, are sent one by one through a double slit setup. This shows the results after 50, 200, and then 2,000 photons have passed through the double slit. And we get that exact same banding interference pattern. So if we ruled out that the light particles could be interacting with each other, does that mean that they are interacting with themselves? Does each particle somehow split in two as it passes through the double slit? The next illustration shows a test for this. We can put some kind of photon detector immediately behind the two slits to tell which slit each photon passes through. However, when we do something like this, the interference pattern goes away. We only ever see the photon go through one slit or the other, and there's no sign of splitting. Light appears to have both wave and particle-like features, and is impacted by observation or measurement. And these are some of the core scientific and even philosophical ideas that hook people into studying quantum mechanics. And as we go on and look at other illustrations, often they link back to some of these core ideas here. Later on, we get to an illustration of the Schrodinger's cat thought experiment. This is a little different to Schrodinger's original setup. In this one, we have our polarizer from earlier chapters. The incoming photon is polarized at 45 degrees, so quantum mechanics treats it as a superposition of horizontal and vertical possibilities. The device separates these possibilities into two paths. The horizontal outcome on the dial here leaves the cat alive, whereas the vertical possibility triggers a lethal device. The point here is that the detector translates a tiny quantum event into a larger physical outcome. The caption says, "Does quantum physics imply that until the box is opened and the state is measured, the cat is neither alive nor dead?" This dotted line is showing that this is a superposition of possibilities until measurement collapses it and leaves just one direct path taken by the photon. It's a comment on the view of a superposition. When we're talking about tiny things like particles being in a superposition of different possibilities, that can seem fine, and we're just talking about things like photons. But this thought experiment is asking, where does that superposition stop? Does it stop at the detector, at the cat, at the person who's opening the box, or does it depend on the consciousness of the observer who is opening that box? Schrödinger's original version of this thought experiment used radioactive decay instead of polarized light, but this whole book has been talking about light polarization so far, so they've used that as their example. But radioactive decay is also a quantum process that has the same questions of randomness around it. Einstein was really bothered by the nature of quantum theory, and he had some famous debates with physicist Niels Bohr over it. Some of these debates occurred around the 1927 Solvay conference, and this drawing here is based off an original from Bohr's notes after that conference, talking about a theoretical device that Einstein had suggested to him. This idea of Einstein's is kind of a single slit screen on springs to go in front of a double slit, and it would theoretically allow you to deduce the path that a photon's going to take, whether it's going to pass through the upper or lower of the two slits after this. The caption says that the path taken by a photon could in principle be deduced from the direction of recoil of the slit, as indicated by the pointer. But Bohr showed that provided the slit obeys the laws of quantum physics, such a measurement would destroy the interference pattern. This one is again just a thought experiment and not a real physical device, but there have been some recent physics experiments that are a kind of recreation of this idea, including this paper, which was using a single atom in an optical tweezer as the movable slit. This next book is a classic undergrad textbook. It's called Introduction to Quantum Mechanics by David Griffiths. It starts by talking about the wave function, which is something that you get by solving the Schrödinger equation. It describes the state of the particle. The square of this wave function is the probability of finding a particle at a given point at a certain time. This is what they say a typical wave function looks like. The particle would be relatively likely to be found near A and unlikely to be found near B. If you want to find the actual probability of finding the particle in any given sliver, say the shaded region here, dx, you'll want to find the area under the curve, or the integral. The next illustration shows what happens when we take a measurement. It is the collapse of the wave function, showing that the particle was found at point C. This book is mostly math and not a lot of illustrations, but here's one in chapter 10 on the adiabatic approximation. It shows a lady carrying a pendulum in a box. It says, if the case is transported very gradually, the pendulum inside keeps swinging with the same amplitude in a plane parallel to the original one. This is relevant to quantum mechanics because if you change a quantum system slowly enough, then it can stay in the same quantum state as it evolves. Here's an illustration of that. In the first picture, a particle is in a ground state in what is called an infinite square well. If the wall of this box that the particle is in were to move slowly, then the particle can remain in its ground state. However, if the wall were to move rapidly, the particle's state would be disturbed. This theory is relevant to learn about for molecular physics, where electrons are quantum particles that move quickly, whereas nuclei are much larger and slower moving in comparison. So in this approximation, you can treat the nuclei as being fixed and solve for the electron motion, and then let the nuclei move slowly, and the electron motion should remain in the same states. This book is Quantum Physics of Atoms, Molecules, Solids, Nuclei, and Particles by Eisberg and Resnick. This illustration here is a good reminder of what wave superposition really looks like. If you were to add up all of these wave functions here, you would get a superposition that looks like this. These are 7 different cosine waves, and even though they individually don't have a point of higher amplitude than the rest, when you add them together, the resultant wave does have varying amplitude. And there's lots more to do with solving the Schrödinger equation, especially as it relates to a square well. This is something where the particle is trapped in only one dimension, such as only in the x direction. In a case like that, the solutions to the Schrödinger equation give us the different allowed energy states of the particle, and these are represented by n. So n equal to 1, 2, 3, and so on. These are the different states that the particle can be in. And when illustrated, these are different waves that still fit within the well. The second state has more wiggle than the first, and the third has even more. The important idea is that the particle can't have any energy at once, only certain wave patterns would fit, and so only certain wave patterns are solutions, and there are discrete energy levels that a particle can have. This is a core idea of quantum mechanics, but that's only for a one-dimensional situation. What about for something three-dimensional like an atom? Well, that's when we get into this chapter on one-electron atoms, such as the hydrogen atom, which has one electron around a nucleus. But since it can move in 3 dimensions, the wave function now depends on 3 variables. And when we solve the Schrödinger equation, we get a solution with 3 components. These are the quantum numbers, often denoted n, l, and m subscript l. These indicate the 3 different ways that a 3-dimensional wave can vary. Take a look at this illustration here. These are an artist's depiction of probability density functions for a 1-electron atom, such as hydrogen. This is like the wave function, but drawn in 3D. The dark areas are where you're more likely to find the electron, and the light areas are where it's least likely to be found. But on any given measurement of where the electron is, it could be anywhere in the cloud. You can see the quantum numbers for each of these drawings. Here is n equals 1, and L and ML are equal to 0. It's a pretty simple little cloud clustered around the nucleus. But increase n to 2, that's now a higher energy level, and the radial size of where you could potentially find the particle has increased. And n equals 3 comes at an even higher energy level and bigger radius. The quantum number L controls the angular shape. So when it was 0, that was just spherical. But if L were to be equal to 1, we'd get more of this donut shape, where the particle can only be found at a certain radius away. ML controls the orientation around an axis. These are all also possibilities for n is equal to 3. A higher n value means there's more energy and more potential radial structure. Because with a higher n, you can also have a higher L value, and this diagram here shows how L impacts the shape of the orbitals. With the one-dimensional case, it was like a string that could vibrate in certain stable patterns. And in 3D, there are still these certain stable patterns labeled with these quantum numbers. This book is Molecular Quantum Mechanics by Atkins and Friedman, and it's the only one with a bit of color in the illustrations. This is a nice illustration of those potential energy levels for the one-dimensional case, the probability distribution of a particle in a box. We've got n equals 1, 2, 3, 4, 5, and 6. Now, we shouldn't forget about the 2-dimensional square well. There's some illustrations of it here. Potential wave functions that can fit inside of a 2-dimensional square. It talks about degeneracy and how some of these are the same as each other, especially if you're just swapping the x and y axes. Instead of a one-dimensional vibrating string, this is a bit like waves on a vibrating drum. In the 3-dimensional case, we're no longer trapped on a square or a line. We're now bound by the attraction to the nucleus itself. This illustration is a little similar to that black and white one from the other book, but we have to remember this is not the literal shape of the electron cloud. This is just a map of the probability. The electron itself isn't smeared out in this shape. This is just the potential places where we could find it. A few pages later, we have this illustration, which is showing the different shapes caused by different values of the L quantum number. But in the language of chemistry, these different values of the L quantum number are referred to with letters. We have s orbitals, p orbitals, and d orbitals, corresponding to L equals 0, 1, and 2. And combining that with the ML values, creating these orbital names that chemists are actually likely to use. This book really tracks the transition from fundamental quantum physics into chemistry. In this book, Atoms and Molecules, A Quantum Theory by Richard Bader, there are these topological maps, which are downstream a few steps from the orbital diagrams we just looked at, but a lot of atoms have more than one electron, and when atoms come together to form molecules, it doesn't make sense to think about individual electron clouds, and instead you can calculate an electron charge density, which is for the whole molecule. This diagram here shows a relief map charge density for the tetrahedrane molecule C4H4. The high peaks is where there's a lot of electron density, and those are the carbon nuclei. The smaller bumps are around the hydrogen nuclei. The molecule on this page is B2H2. These are not wave function diagrams, these are just illustrations of this total density of electrons. The saddle points indicate where the bonds are. This book by Hughes is pretty interesting. It's The Structure and Interpretation of Quantum Mechanics, and there's a chapter on quantum logic. They start with a classical example where there's two coins, a quarter and a penny, and this illustration here, figure 7.3, are all the possible outcomes for flipping these two coins and how they relate to each other. The most general truths are at the top, going down to the more specific. So we've got P here, which means that the penny landed head up, and linked to that is P and Q, so the penny and the quarter landed face up. That is inconsistent with the outcome that the quarter and the penny landed face down, and so those nodes are not connected to each other. This whole structure is called Boolean algebra, and it's only shown here as an example of what's not possible with quantum logic. Asking if the penny and the quarter showed heads or tails are questions that have definite yes-no answers at the same time. But in quantum mechanics, for example, you might want to ask, does an electron have spin up in the z direction? And does it have spin up in the x direction? But since measuring one of these can disturb the other, there isn't a definite answer to both that's just waiting to be revealed. And you couldn't form a structure like this with these quantum questions. Quantum logic forms different kinds of structures, and a few of them are shown in this book. In quantum logic, each possible yes-no outcome is represented by a subspace. In this way, the logical question of asking or actually has a geometrical meaning. Suppose you have two quantum events. You could call them Lx and Ly. This might be a line from the origin towards the x direction and another line from the origin towards the y direction. They might indicate a quantum event like, is the electron spin up along the x-axis? In ordinary set logic, Lx or Ly would just mean one line or the other, but in this quantum subspace logic, Lx or Ly actually means the larger space that contains both of these possibilities. That is the plane spanned by these two lines. It contains not just purely Lx and purely Ly, but superpositions of them. This figure 7.8 is showing a kind of logical lattice that would work for quantum events. Here things are subspaces of R3, which is at the very top. That's all of real space. In real quantum mechanics, though, everything would be a subspace of something else called Hilbert space. But anyway, we have the first line, which are planes in this space. And beneath that are the lines themselves in each direction, and then at the bottom is a set containing 0. And then exploring what possibilities connect to each other is the topic of quantum logic, something that I don't fully understand. I think I only understand it well enough to say what I've said about the difference between it and the classical example. But there are some more interesting looking diagrams further through this book, like this 14-element orthomodular lattice that has got something to do with observables of quantum systems. We've got time to take a look at one application of quantum mechanics. This is Quantum Technology by Gerard Milburn, and it contains this cruel and torturous technology known as Sisyphus cooling, where that torture is directed towards an atom. This is a way to cool down atoms by making them expend energy by always rolling uphill, just like the Greek god Sisyphus. Here we have two lasers pointing in opposite directions, which establish a kind of standing wave. The atom is moving through this light, and there's some clever way to suddenly switch the atom back into a valley every time it reaches a peak. In this way, the atom is essentially always rolling uphill. It loses energy and speed every time it does this, and with an atom, speed is temperature, so this is a way to cool something down. The atom is not physically climbing a hill. These hills are representing an energy landscape. A scientist might want to do something like this to study quantum behavior, to make atoms easier to trap, or to make Bose-Einstein condensates. Just quickly flicking through the other illustrations here, we can see principles of a magneto-optical trap, a trampoline for cold atoms, an electron turnstile, and even some kind of device for quantum spying. There is, of course, also the elusive quantum computer and ways to build up those circuits. I chose to look through illustrations for this video because they can be a useful way to learn visually, but sometimes just looking at illustrations isn't enough. It can be useful to have some help in deciphering what's going on. Brilliant have just announced a new tool to help learners understand visual math and coding problems. Their new update is like an intelligent personal tutor. When trying to understand unfamiliar concepts, I find it hard to know if I'm on the right track, and that's one thing I appreciate about Brilliant. You make little mistakes and then get guided back to what's going on. Brilliant has always been very visual, but now it's much closer to having a tutor sitting right there with you as you learn. It can see what you're working on, draw diagrams, and ask guiding questions. What feels the most exciting to me is that the tutor won't just tell you the answer like some other AI tools might. Instead, it's developed by experts in pedagogy, or how people learn best. With that knowledge, it will try to make the right interventions at the right moment. It can identify what's causing your confusion and map that back to a common misconception so you can more effectively close those gaps in your knowledge. Here's an example from the course Thinking in Python. It wants me to complete this code block. We'll go with this to start from the most recent. And then I can't remember how this works.
Think of the in keyword like checking if a letter is in a mailbox. Which of these acts as the mailbox that holds the files?
So we'll go...
Exactly.
All right.
Since attachments holds the files, the print should happen when malware is in attachments. Go ahead and hit check to run your code. Not a single mistake. Crushed it.
Click the link below or scan the QR code to try Brilliant's tutor for free. You can upgrade to premium to unlock all the courses. And right now, viewers of my channel can get 20% off an annual premium subscription at brilliant.org/Tibees. Thanks Brilliant, and thanks to my Patreon supporters for making this video possible. A special shout out to today's Patreon cat of the day, Little Bit.